So in fission, those nuclides, the nuclides that are not themselves fissile, but become converted to fissile nuclides upon absorption of a neutron are called fertile. For example, uranium-238, a non-fissile isotope, absorbs a neutron and eventually becomes plutonium-239, which is a fertile isotope. In fusion, two or more light nuclei are combined to form a heavier nucleus. So such reactions are possible only if the nuclei possesses sufficient kinetic energy to overcome the repulsive forces and are able to reach each other. As with fission reactions, fusion reaction energy release results from the conversion of mass to energy. So in this fusion reaction on the bottom of the slide, you can see that they all involve isotopes of hydrogen. So we have on the reactant side two elements of deuterium that yields tritium, as well as energy from the fusion of the two atoms of deuterium. And in radioactivity, you have what we would have the spontaneous decay of a nucleus by emission of one or more small particles. A key word in this definition is spontaneous, since unlike fission and fusion reactions, the instability of the nucleus of a radioactive isotope is the causative effect. Isotopes that occur naturally are stable in most elements, but elements with atomic numbers greater than 84 have no stable isotopes. And a few isotopes of elements with atomic numbers less than 84 are also unstable. So isotopes artificially produced in particle accelerators and nuclear reactors are all unstable and number in the thousands. The time required for an unstable nucleus to decay is indeterminate, but among a large cohort of the same unstable nuclei, there is a statistical probability that a certain fraction will decay within a specified time. So we look at something called a half-life, right? So that would be the time required for half of that mass to decay. So if we're looking at this equation, N is the number of radioactive isotopes present at time t, and N0 is the number of isotopes that are present at time 0. So if you can see over time, you can see an exponential decay in the number of isotopes over the length of time defined by the number of half-lives. The half-lives of different isotopes differ by many orders of magnitude. For example, the half-life of polonium-212 is only about a third of a second, whereas the half-life of uranium-238 is about 4.5 times 10 to the 9 years. In regards to the types of radioactive decay, there are a few, so we're going to look first at alpha decay. An alpha particle is the nucleus of a helium atom and is written as 2He4, so that would be again an isotope of helium, right? So we would have 2 protons and 2 neutrons. Alpha decay occurs when an alpha particle is we have radium-226, which emits an alpha particle and reduces down to radium-222. So in alpha decay, Z is reduced by 2. Z again being the atomic number, and A being the mass number is reduced by 4. In the above reaction, radium is the parent and radon is the daughter. Most of the energy is dissipated in this case, close to the emitting nucleus. So alpha particles possess limited penetrating ability, a few centimeters in air, and a much shorter distance in solids, that about the thickness of a sheet of paper. Unless alpha emitters are ingested, they pose little health danger. Then we have beta decay. Beta decay is a transformation of a neutron in the nucleus into a proton and an electron, which results in the emission of the electron in order to maintain the charge balance of the nucleus. Here we have, in this reaction example, lead-214, which yields bismuth-214, and an electron, and then also a neutrino, which is a small neutrally charged particle that carries about 5% of the energy of their reaction. Let's look at a quick example problem here. This example problem reads, a radioactive isotope, iodine-135, decays by beta emission into xenon-135. Determine the time required for the number of iodine atoms to be reduced by 90%. The half-life is 6.57 hours. So again, you want the number of actual isotopes over the initial to be 10% of where they started, right? That's if you want to reduce it by 90%. It is telling us that the half-life is 6.57 hours. Using the equation from the prior slide, looking at the half-life, so we want to reduce this. So again, we want that to be 10% of where we started. That would equal the exponential of negative 0.69315 multiplied by time t over the half-life. If we were to do our exponential math, we would find that it would take 21.8 hours.